I just wanted to thank you guys for coming, and also I would like to thank Professor David Ingram for inviting me. I have had a lot of fun here, and it's fantastic. I hope to come back soon. Even though I'm part of MERIC, I'm leading one of the, and I'll tell you a little bit more about it right now, but I'm leading one of the research areas. I wanted to talk to you today about something totally different, just because I like this topic. So I'll try to be, I'll try to explain everything from the beginning if you're not familiar with sediment transport, which is part of the things that we do. This work actually is a collaboration we have had for a few years with, well, that's my PhD student, Christian Gonzalez, but also from two friends from the University of Notre Dame in the US, and Joe from the Naval Research Laboratory also in the US. So within my research topics, in what we do in our research group, we work mostly on marine and hydrokinetic energy. I'm also in charge of the wave part, but in that area has been developed mostly by my colleague Rodrigo Cienfuegos. I'm also part of a natural hazard center in which we are studying flooding in mountain rivers, which are really fast, and they have a lot of sediment transport too. They produce a lot of sediment transport. And this is a topic that I'm going to talk today about multiscale physical processes in fluvial environments generally. About MERIC, well, we just inaugurated the center in June in a coastal station of my university. This is a consortium between the industry, basically DCNS in our case, and the university I work in with the University of Australia in the south in Valdivia. And I'm leaving this area, but MERIC has several areas that people are working from what we do to biofouling, marine corrosion, ecosystems. We're going to install a test bench in the ocean and develop some guidelines, social aspects, everything across the board. What we've been doing as part of, I have been lucky enough to work with bright people just like Daniel, so we're doing some simulations, experiments, and field work in the area. And if you guys want to go to Chile, we're going to have this workshop in November, so there's still time to submit your abstract. I'm also part of the Center of Natural Hazards. We've been focusing on floods. At the beginning, we had all this plan made for analyzing floods in the mountains, but last year in the Atacama Desert, where never rains except for last year, towns like Chañaral, like this one. This is a picture from Google Street View. If you go to this place right now, you're going to see that it looks like this. It was a huge flood. So we did some forensic work to try to understand what had happened, what had produced from the meteorological point of view up to the propagation of the flood in the terrain. So we have done some very cool experiments trying to understand what was the process, why all these towns got flooded, what are the consequences. And this is the work we had initially planned. We have developed models to couple sediment transport and see how the city of Santiago is going to flood the next time that something big comes. And we are also collaborating with professors from the electrical engineering department, trying to monitor with these very simple and cheap stations, try to know exactly what's happening in the mountains. So we have been installing this and develop an early warning system for floods. And what we do here in the physical process, we go from what I'm going to talk about today, DNS of particles, to things that occur at the reach scale in the river, to sedimentation, morphodynamics in rivers at the scale of kilometers. This is a paper we published last year on the interactions of morphodynamics and geochemistry in rivers that have a lot of pollution in the north due to mining. So all this about particles started a long time ago. When I was doing my PhD, this was just my hobby. I started just because I liked it. I started investigating about particle motion in these flows that occur at low Reynolds numbers, but they have chaotic properties. This is not turbulence. These are even steady flows. Very simple flows is called one of the von Karman flows, in which you have the leads in a cylinder rotating in different directions. So at some point, for a low Reynolds number, you develop this donut type of vortices, right? So the way of analyzing these flows is Lagrangian. So I started looking into, this had nothing to do with my thesis of what I was doing, is just, I started looking at Lagrangian dynamics of particles in these chaotically advected flows. And you can start seeing, when you plot these point coordinate maps, it's just every time a particle pierces this plane, you start seeing where the particles go, right? So here I put particles of fluid, which are the blue particles, and the green and red have different properties in terms of inertia and weight. And you can see that there are some areas of the flow that have a large mixing capacity, even though it's not turbulence. And so you can use these flows to mix with great efficiency, even though this is not, or you cannot produce turbulence. So, and these toroidal vortices, these donuts, are barrier to transport. So you can see that there are some areas that are integrable areas with no mixing in between this chaotic sea. Right? So we started looking into the dynamics of particles and how inertia and gravity produce changes in the dynamics of particles in these cases. So then one of the things that we did, that's why the hybrid model started, the DES model started, is to look at the horseshoe vortex, which is the vortex that develops when you have a turbulent boundary layer and an obstacle, like a pile or something like that. The dynamics of this vortex, especially at high Reynolds numbers, is very, very complex. And the only way to resolve this at real-life Reynolds numbers was to use a hybrid model, so we didn't have to resolve the tiny vortices of the boundary layer, but at the same time capture the dynamics of the vortex. So for the first time, using DES, we were able to understand the dynamics of the horseshoe vortex, which is comprised of several vortices that actually merge. There's I don't have all the time to explain you. It's a great story. There's a centrifugal instability that develops. You know, the vorticical surface. The serpent vortices are formed, which are swallowed by the horseshoe vortex, and then everything explodes. So it was fantastic. We were able to reproduce all the dynamics of the horseshoe vortex that actually drives erosion and scour around piers. So since we knew, once we were able to understand the dynamics of the horseshoe vortex and we were able to resolve it, we started looking at sediment transport. So since I had worked already with particles, I tried to see what was the effect of this vortex on the particle motion. So if you go to the classical literature on turbulence modeling, this is the Shields diagram. Okay? Shields was an American researcher who did his PhD in Germany, and after he finished his PhD, he retired to do something else. So what he did was to relate and develop this diagram in which you have the particle Reynolds number versus a non-dimensional shear stress, which is called the Shields parameter right now. And he defined this curve. Under this curve, supposedly there's no motion, and above this curve you have sediment transport due to the turbulence, right? And this is a very complex problem because you are actually this should be a band, in fact, in which and turbulence sometimes can move particles. So it's difficult to define exactly what is the initiation of motion in these conditions, right? This has been a problem for a long, long time in sediment transport research. And most of the formulas that are used for bedload transport, sediment transport near the bed, assume that this is a sharp transition, which is probably not. In fact, there are some experiments in the 70s in the St. Anthony Falls lab at the University of Minnesota. There were experiments for a very, very low Shields parameter, and they waited a month, and you still had sediment transport. So all this time, from the early 20th century, there has been this controversy between this vision, which is mostly what Bagnall and other people have developed, and Hans Albert Einstein or Einstein Jr.'s vision, which is, you have to see it or look at this problem as a probability problem. So what I did was I started looking into the dynamics of particles. The flow now goes in this direction. This is just one of the examples of the simulations we performed, but the upstream flow cannot move particles. We are way below the critical shear stress. But the horseshoe vortex, being so big and interacting with the bed and the cylinder, increased the shear stresses by an order of magnitude. So if we perform this simulation, you will see that the horseshoe vortex can actually transport the particles downstream, right? And move them. Obviously, the particles that get in the area outside the horseshoe vortex will not move because the turbulent boundary layer is not capable of mobilizing them. So one of the things that we did is that, or realized, is that, first of all, the transport become very intermittent. Okay, we're very close to the threshold of motion, to this critical shield stress. So groups of particles, and this is just a static figure to show you that groups of particles get detached and move, but sometimes nothing happens. There are particles that just slide on the bed or just remain there for a long, long time. And also, you get these streaks, which we were also able to reproduce a lot of experiments that had seen these particles get aligned and on top of the bed under these conditions. So we decided to start counting particles. We defined a vertical plane and started counting how many particles cross that plane. What was the transport? Because that's what you actually can measure in the lab. And if you look at that, you see that there are huge transport events, but then there are periods where nothing happens. Silence. No particles are transported. Then you have smaller transport events, and then nothing happens, and then long periods where nothing happens, and then everything is intermittent. And if you look closer at this, you see the self-similarity up to the resolution of one particle. This is actually a well-known fractal curve based on the Cantor set. It's called the Devil's Staircase. And I got really happy, because I work at the Catholic University of Chile and I get to work with the devil. So it's a lot of fun. This is the devil. You cannot actually fit a statistical distribution to this type of curves, right? It's a fractal, similar curve. So one of the things that we realize is that near the threshold of motion, bedload is very intermittent. If you look at what you actually can measure in the lab, bedload is very intermittent. These are the most common conditions in nature. You don't have, a sheet flow of the entire bed all the time. Most of the time, the rivers are maintaining this condition very close to the critical. And what happens really, it happens at different time scales and spatial scales, from the scales to the particle up to the formation of bed forms and all that. I don't have time yet, not right now, to tell you, but from this Lagrangian analysis, we develop an Eulerian version of the same thing, and for the first time we couple the bed with the horseshoe vortex, and we resolve bed forms for the first time in a 3D model. I can talk about that later, but it's not the purpose of this talk. So now we wanted to understand, in fact, what happened when you don't have a cylinder, but still the boundary layer can transport sediment. So the main objectives of this investigation was to understand the dynamics of the turbulent boundary layer and the interaction of the particles in a mobile bed. Now the boundary layer is performing the transport, not this horseshoe vortex, and try to understand what are the mechanisms that produce intermittency and characterize the bedload flux in these conditions. So what we are doing is solving the Navier-Stokes equations in what is called a two-way coupling manner, which means that the velocity and pressure determine forces on the particle momentum equation, but these forces are also felt by the fluid. Okay? So they are both interacting. So we solve for each particle the trajectory and the momentum equation, and also we solve the Navier-Stokes equations with DNS. If you're not familiar, DNS means we are solving the whole Kolmogorov spectrum from the largest scale, which is the size of the domain, to the Kolmogorov scale, which is the smallest, at which turbulence or kinetic energy dissipates into heat. Okay, viscosity does that part of the work. so we developed this DNS model based on the method of Richter and Sullivan, which considers the spectral method in the horizontal directions and finite volume in the vertical. And in time we use a third-order Runge-Kutta scheme, and the particles are calculated with a fifth-order Lagrangian polynomial interpolation, and we use DEM, in which we consider the collision among particles with a scheme that dissipates the energy and gives you what happens after a collision in the tangential and normal direction. So the simulations we carry out were in a very DNS is very, very expensive. So this is the largest domain we could handle. 4 centimeters tall. These are the other are the horizontal directions, and we have 50,000 particles in this case, just laid on top of the on the bed, right? So under these conditions, we can only get to a Reynolds number of around 3600. These are the other conditions of the particles, the coefficient of restitution and Poisson of the particles' collisions, and the density of the particles on the fluid, the Stokes number, and all the characteristics that define this case in particular. So what we tried to do was to, this is again the Shields diagram. Don't care about this. This was only just to check how the model was working on. But we fixed the Reynolds number of the flow, of the Reynolds number of the particles, and we tried different values of the Shields number around the curve given by Shields. So what you see in each flow, we resolve the flow on top of this particle layer, and actually see what happens. I forgot to tell you, but the lateral boundary conditions are all periodic. So any particle that comes out gets seen immediately upstream. Right? It's like modeling a small stump on a riverbed. So we can resolve now. This was one of the first simulations we carry out. The next one you're going to see is this is faster than, because it's really boring to see particles moving every 2 minutes. But what happens is that the particles get trapped in these protective pockets inside the bed. So they start vibrating, and then they jump. They start jumping, and you see how this intermittent bedload transport develops. So we were able to look now at the coupled flow and particle thing. So you see that all the particles that are gray are not moving, have zero velocity. So when you have these hairpin vortices developing at the boundary layer, when they get up, they allow faster fluid to rush near the bed. So you have this transport event, again, in which groups of particles are transported downstream as the flow develops. So, oops, it doesn't seem very well, but this is for different, for different Shields parameter. We started looking into the statistics of particles, seeing how the streamwise velocity of the particles started increasing as a function of the Shields parameter. Right? You will see here that we had to set up a threshold to analyze this, because negative velocity is when the particles start bouncing before jumping. So you see that the backward motion of the particle is captured by the histogram in this case. Then we have what is called the activity on the bed, which is the total number of particles in motion at every instant in time. You know, I imagine probably that Shields, the thing is that Albert Shields left his thesis abandoned in Germany, and then Hunter Rouse, which was the director in the lab in Iowa, found it, translated it, and made it famous. Everyone now uses the Shields diagram, and Shields didn't even know. He knew many, many years later. So I imagine Shields that defining at what point you decide that this is the initiation of motion, right? When the first particle moves, or when a significant number of particles are moving, or when the entire bed is moving. That's really difficult to define. Actually, I really think it's impossible in this case. But you start seeing that how the behavior changes So when the Shields parameter is very low, basically no particles are moving at the same time on the bed. As the Shields number increases, you start having a distribution of particles that are moving. So what we did was to feed a gamma distribution for the PDF of activity. This is the gamma distribution, if you remember. So when this parameter k is smaller than 1, you get this exponential type of behavior. When k is larger than 1, you have this log normal type of behavior, which means that in this transition, there's always a particle at least moving in some point of the domain. And this is just a scale parameter saying describing the stretching of the PDF, which means that the more intermittent, or you can find larger velocities as the Shields number increases. So you see how the k parameter increases and how the beta parameter also increases with the Shields number, which is the x value. So you see that at about this Shields number, 0.067, you can start saying that there will always be a particle moving in some place, right, of the domain. Sorry. The particle jumps also. You start seeing that as the Shield number increases, you start seeing these are the PDFs of particle jumps. This is the same PDF but in log scale. So you see that the tails become longer and longer. You can have big events of particles jumping a great distance as the Shield parameter increases. And again, if we start collecting the sediment flux, using this as an experiment and measuring how many particles exit the domain, you get again more devil staircases with different properties. So you see that you get these periods where nothing happens, no particles exit the domain, and then you start seeing more and more particles, or big events and smaller events, depending on this parameter. So the only way of characterizing this is to characterize the scaling of since it depends on the time and length scale. We can scale the sediment flux depending on the magnitude of these transport events. So if you define the magnitude of an event as the mass between two steps of the staircase, you can analyze this at different time scales, and you can see if there's a scaling relationship. Actually, this is what is called the fractal dimension of the transport event magnitude. And if you have experience with this, the only way to characterize this, the moments of this transport event magnitude are related to what is called the multifractal spectrum of transport, which is the only way to analyze this. The momentums are related to this singularity of multifractal spectrum to what is called the Lagrangian transform. So you see that we get these different multifractal spectrums as the Shields parameter increases, and the fractal dimension, which is this the peaks of these distributions, also increase with the Shields parameter. Now we have completed this plot. We have more points here, but you see that the sediment flux, it's very intermittent, and you see that the fractal dimension is always less than 1, which means that there's no differentiability. You see continuously steps and plateaus at different time scales, but then at a certain Shields parameter, the fractal dimension becomes 1, which means that you have a continuous transport. There's always, at all the time scales, there's always particles exiting the domain. So you can identify, it's really difficult to identify initiation of motion, but at least you can say, it will be in an intermittent regime, or actually you will have always one particle exiting. It will seem continuous, which means that the fractal dimension is equal to 1, at least, in these conditions. So the conclusion, we used a two-way couple in which we combine DNS and DEM to analyze the dynamics of sediment transport and try to characterize the transport with the Shields parameter and see how the properties of the sediment flux change under these conditions with a different characteristics that are through we can describe the sediment transport flux. And this is actually the first time that we have been able to connect all these loose ends. So in the future, what we expect to do is to incorporate, for instance, different sediment diameters. What happens, what is the effect? And some of the things have been done in experiments, but what is the effect of having a bimodal distribution of sediment diameter, right? What are the effects on the initiation of motion, on the intermittency of transport? And that's something that we now can do with this model. See what are the real parameters that then can distribute the transport regime. Is it the Shields parameter only, or it will depend on the Stokes number of the particle, on the Reynolds number of the flow, on the D star, which is a non-dimensional diameter of the sediments? And then, this is the long-term objective, is to see if we can use this information to improve the prediction of sediment transport in real conditions. See if there's something missing that we can add and improve the prediction of bedload transport that is actually used in real flows. Thank you very much for your attention.